Okay guys, Assalamualaikum. So today is a video lecture for chapter 1, the first part of chapter 1, parameter estimation. So it's more to theoretical part, so I try to finish everything in chapter 1 by today so that we have a discussions on Friday regarding the examples and the mathematical derivation and solution. Okay, so this the subtopic for chapter 1. There are 4 parts. The first one, introduction to parameter estimations, and then least square, LS parameter estimation, and then offline or batch least square estimations, and the last one is online, recursive least square estimation. Okay, the definition for a parameter estimation is a process of determining the value of the coefficient relating different signals in a system, and you have to know how to differentiate between signals and a coefficient. Okay, so let's say we have one equation, yk equal to a uk plus b. So signals are yk and uk, while coefficients are a and b. So a and b is a coefficients, is a constant value, while signals is a varying uh, varying parameter. Okay, so if we can tabulate the signals and the coefficients regarding the equation given, so signals is yk and uk, and coefficients is a and b. So you have to know how to differentiate the signals and coefficient before we go to the next step. So in the control system, parameter estimation aims is to obtain the coefficient of the plant of the transfer function that to be controlled. So the estimation process usually involves processing the input and the corresponding output signals of the plant. So figure 1.1 show the parameter estimation process. So as you can see, there are two blocks, systems, GS, and parameter estimator, where the input signals is the input for the system as well for the parameter estimator. And output signals is also input for the parameter estimator and the output for the system GS. And we also denote the estimated value of the transfer function as G hat S. So these input and output signals are fed into parameter estimations or estimator, which process them to produce the estimated transfer functions of the plant, G hat S. So the estimated transfer function is usually denoted by a hat, usually hat. And so this is the process parameter estimation. So the need to estimate uh, the parameters of the plant to be controlled arise from two conditions. For example, when the parameters of the systems are time varying, maksudnya berubah-ubah, and tracking of these variations is needed. And the second condition is when the system models is difficult to obtain, for example, chemicals processes or complex dynamical system. This square parameter estimation is one of the most popular estimations algorithm. So Carl Friedrich Gauss first formulated the least square estimation method in 1795 for astronomical computations purpose. And Then next, variations other methods are also available, such as the Bayesian method in 1968 and the maximum likelihood method in 1918. The DT, discrete time, D-square, is a basic technique for parameter estimations. So before that, what is the difference between discrete time or DT and a continuous time CT? Okay, you have go through this too during signal and system course. So this as a revision because we will use discrete times equations for chapter 1. So a continuous time signals has values for all points in time in some intervals. So for the graph, it looks something like this. Okay. And for discrete time signals, it only has value for only discrete point in time. So you can see the difference in terms of the definitions and graph between continuous time signals and discrete time signals. And before this method is described about least square parameter estimations in details, some of the important notations are defined. The DT least square is a basic technique for parameter estimation. Before this method is described, some of the important notation are defined. K is a discrete time index. UK is the system input at discrete time K. YK is a measured system output at discrete time K. Theta K is the unknown parameter vector to be estimated. Theta hat K is the estimated of theta K. Phi K is the vector of input and output signals and possibly their delayed signal. Zeta K equal to Yk minus Y hat K is a residue. Y hat K is the estimated output signals. There are two ways of estimating parameter using least square algorithms. Number one, offline least square estimation or batch processing. Number two, online least square estimation or recursive least square RLS. Offline batch least square estimation. Offline least square estimation can be used to estimate system parameters when at least a set of input data into the systems and a set of the corresponding output data are available. Consider the discrete time transfer function yk over uk equal to b naught plus b1z minus 1 plus b and bz minus nb over 1 minus a1z minus 1 minus a2z minus 2 minus a and az minus na. That can be written as yk equal to these equations. So you can arrange from this equation to this equation. Okay. The equation from the previous slide then arranged in the regression equation form as follows. Yk equal to yk minus 1, yk minus na, uk minus na, and b times a1, a and a,
B1, B and A. So we get YK equal to phi transpose K theta, where here is the phi transpose K, and here is the equation, the matrix for theta, where YK equal to Y hat K. Theta K is determined such that the output calculate from the right hand side of this equation, Y hat K equal to phi transpose K theta, match as closely as possible with the measured K in the cent of the least square. This is done by minimizing this equation, where n is the total number of data available for estimation, and En is equal to Yn minus Y hat n equal to Yn minus Phi n theta. Therefore, En equal to zeta 1, zeta 2 until zeta n, while Yn transpose equal to Y1, Y2 until Yn, and phi n equal to phi transpose 1, phi transpose 2 until phi transpose n.
So J is minimized by setting dj over dt equal to 0. And this derivation will give equation that we will use, theta hat equal to phi transpose phi minus 1, phi transpose yn. So this is the equation that we will use in order to find the estimated unknown parameter value. Okay, so the detailed derivation, I will give a extra video lecture. So you know how we get the equations. It's not necessary for you to understand since we just use the equations. Okay, so these the examples for offline parameter estimation. We will have a discussion on Friday. I will go through together with you one by one, so that you know the flow and the procedure in get theta hat k. Theta hat k is vector of A and B, the estimation of A and B. Okay, if you want to try it first, it's up to you. Since I will not give any examples of the solutions, since we will do it together. It's good for you to try it first, and then we have discussions on Friday.
Okay, type number 2, online recursive least square estimations. In online processing, the parameter is estimated in a recursive manner as the observations are obtained sequentially. The recursive least square algorithm is developed based on the batch processing algorithm using symmetric manipulations. This significantly reduces computational time and effort since there are no matrix inversion involved. Also, since the estimation can be done at every sampling intervals, it allows the tracking of any change that might occur in the system. RLS can be used to estimate parameter of a transfer function in an online manner where the estimated parameter are updated at every sampling intervals. Okay, consider a discrete time dt system in the form that can be written in the regression models. Okay, yk equal to yk minus 1, yk minus NA, uk minus NB times A1, A and A, B1 until B and B. So we rearrange the equations and we get yk equal to P transpose K theta. Okay. The regression equation from previous slide then used in the recursive least square algorithm, whose summary is given in these tables. Okay, we have theta k, where is a current estimate is obtained by adding a correction to the previous estimations. And then LK, L is known as the least square weighting factor, which tell how the correction and the previous estimate should be continued. Zeta K, the current estimation error. And the last one is PK. P is the mark that is proportional to the variance of the previous estimation, and rho is the forgetting factor that determines how fast all data are forgotten. If a rho is 1, so no data will be forgotten. Therefore, if the parameters to be identified are time varying, rho should take a value less than 1. The smaller it is value, the faster all data is discarded. We also assume theta hat 0 equal to 0 and P0 equal to sigma squared, with sigma squared are a very large number normally used. You can find it in the assignment question. Okay, P naught equal to metric 100, in that matrix identity 100. So this data will speed up the convergence process of the estimates to their true values. Okay, the reason why P naught is the very large number. Okay, so this will speed up the convergence process to estimate their true values. Okay, so same goes to this example too. We will go through on Friday. This example for online parameter estimation. So it will be 2 questions we will discuss on Friday. You feel free to try it first if you have your senior notes, etc. And I will go step by step together with you on Friday. Okay, guys. Okay, as summary for least square parameter estimations, there are 2 things that we do. So the least square method find the most probable value of theta k, or we denote by theta hat k, where we minimize the sum of the square of the residual zeta k, and we're also minimizing the cost function j. Okay, so that's 2 things that we do in least square parameter estimation in order to get the unknown parameter, estimated unknown parameter vector. And the number of the parameter depends on the equation given. Okay, so that's all for chapter 1, theoretically part. But maybe there are a lot of questions regarding the procedure and so on. I have go through the equation involved, the notations that you will go through in chapter 1. In details, we have a discussion on Friday. So bila kita buat soalan or examples, baru you nampak lah dekat mana you guna, what is the regression model, etc. So my aim today is just finish chapter 1 so that we have covered 1.1 until 1.4. So you already know the definitions of the definition of parameter estimations, what is the difference between online and offline, and then the parameter estimation blocks and diagram, etc. Okay,
So I think that's all for today lecture. Have a good holiday tomorrow so that we meet again online on Friday. Okay, guys, that's all. Thank you very much.